Okay. Hello class. So this is the final workshop of the module. It's the final official class of the module. And briefly, I'm going to be going through an overview of the course. This may take a while, but I think that it's necessary. Just for everyone's knowledge, you can pass the message on. I'll also announce it. This is not going to be released as a recording just because it's an overview. It's a revision class. I understand that it's a workshop, it's coursework deadline day, and so that causes some complications. But we don't have any more time, so that is the way it is. I'm not presenting any new information here. It's simply information that I provided to you before in the same form. So let me just turn my camera off and share my screen. But it's good to see you for the last time. I'm going to be hosting office hours up until Christmas. So the 22nd is going to be my last office hours. I'll make an announcement, so there's no need to make a note of that. But anyway, let's crack on and let's continue with this. Okay, I'm just sharing my screen. Okay, so just a reminder, Q1 Plus, the coursework submission is here. You just need to submit as a group, and that will be fine. It only needs one person to submit. You can also do the peer assessment. This is particularly important if you feel that others haven't contributed at all or next to nothing. So please let me know. This is the only mechanism or the main mechanism that I can use to take that into account. So please do use that forum. Let me just pass over to the module structure. It's a bit pointless at this point. So we're here, week 15. We have week 16 and 17 of class, of term before the exams. I normally hold my office hours on a Wednesday, and they will continue for 2 more weeks. So just to let you know that. All right. So this is chapter 14. But as I said, it's an overview. You have seen everything I'm about to show you before. So for you in the room and also joining online, just so you know, and this is a note down here, this presentation does not form a comprehensive summary of the module. Other key information is found in the individual chapters. So these are all of the chapters. These timings probably need to be adjusted for next term, but I know that now. One thing that I'm going to be doing is going through all of the chapters, but taking into account this traffic light system. So the selection of slides that I've made are green slides only. Now, I would not recommend, I'll repeat, I do not recommend that you select green slides only for your revision. If you do, you are going to sell yourself short. You're not going to do as well as you can do. However, if you are struggling with the amount of work in the course, if you are struggling to kind of get to grips with all of the concepts, then please focus on green slides. However, if you want to get full marks and do your best, then I would also incorporate yellow slides into that. And I've hopefully voiced that throughout the course, is that there is importance on the yellow slides, as it says here, and as was indicated in chapter 1. So that's just a quick note there. So in here, in chapter 1, it was just an introductory lecture, and it was incorporated many things that we would go on to talk about. The first of those is what is a surface and what is an interface, and how do we define that? So that's the primary aspect of a surface is an interface, of course, is that you know what that is. And hopefully that's clear at the moment. Then there were some definitions about substrates, absorbates, and absorption, and hopefully those are also there. We spoke about physisorption versus chemisorption, and this was a context that we also went through in multiple aspects of the course. Surface tension, again, quite a key principle, and this is also something that I would expect you to be familiar with and expected to be able to talk about. So if someone were to ask you how does surface tension come about, then you would be able to answer that question. And those were the green slides for chapter 1. As I said, most of those things I'm going to come back to in future chapters, but those were the points for chapter 1. So in chapter 2, there were surface-specific matters. So this covered the surface area to volume relationship, which we'll go through briefly, and it gave you some examples. Some of them aren't required, and there was some revision on bonding. So this relationship down here is key. So surface area to volume ratio is proportional to 1 over d, d being the characteristic length. So as you decrease d, get smaller in size, then what you do is you increase the surface area to volume ratio, and this is a reason for it. Here was a worked example and showed you the effect of the 1 over d relationship. And again, to reiterate, this is a key principle that we need to be on top of. Then we did some revision about bonding, ionic, covalent, metallic. We spoke about what they are in broad terms, but fundamentally, you should be aware of these different bond types. Metallic is not so important for the course, as you know. However, you should know what these bonds are, and I'm confident that the vast majority of you do. We spoke about van der Waals forces and dipole interactions, and that included hydrogen bonds. We spoke about dispersive forces as well as repulsive forces as well. And so these are also principles covered in other courses, and these were the terms that I laid them out in here. And this is just a brief summary of the bonding models that we were talking about. Yeah, and so those were the learning outcomes, and that brought us on to chapter 3. And this was going further into hydrogen bonding. I've missed out the learning outcomes for this, but they should be included at the end. Identification of hydrogen bond donors and acceptors, and the definition of what a hydrogen bond is. This is key information. The hydrophobic effect. So why do hydrophobic molecules group together in water? And that should be obvious to you. Amphiphilic molecules. What is an amphiphile? Could you draw an amphiphilic molecule if I asked you to? What is, yeah. The exact structures shown here are not key information, but the understanding of what an amphiphile is key information. Then we started speaking about micelles and how they can be formed. So this is the micelle structure here. We spoke about standard or normal, regular micelles, and then inverted micelles. I introduced the CMC. What is the CMC? How is it measured? What is practically going on when you measure it, and what happens at this point here? That is a saturation of the surface. Okay. Again, reiterating micelle structures, that they can be made of ionic, non-ionic. They can be reversed, as I showed, and they can be rod-like. And then going beyond micelles, we were talking about bilayers, and that was kind of the next topic that we were going to discuss. Also here mentioned was the alignment of bilayers on hydrophobic and hydrophilic substrates. So here's the definition of a liposome. They come in two main varieties, that being unilamellar, one layer, and multilamellar, multi-layers, and then they come in different sizes. As I said in lecture, you do not need to remember these sizes here, as in the precise numbers, but just be aware that they come in different varieties. Formation of liposomes, so how are they formed? They need thermal energy, and they have two phases, so they are solid and gel-like, and they can rearrange. Bilayers can rearrange in the gel phase or gel state to form your liposomes. And this was talking about the significance of packing, and that was the difference between micelles favoring this type of geometry, bilayers preferring this type of geometry, and liposomes preferring somewhere in between. That led us on to talking about the CPP. Now, this should be this is a key principle. You do need to know CPP values, CPP shapes, and the preferred forms. Generally, these make sense. The only thing to learn are these precise values here. Then we spoke more in depth on how you prepare liposomes. So again, this is something that you do need to know. Note that I think that the steps can be rationalized. However, this is something that you do need to know and understand. And here were the learning outcomes. So we spoke about hydrophobicity on the macro scale, hydrogen bonding, micelles, and liposomes in chapter 3. Chapter 4 was about absorption. It was in two parts. These were the learning outcomes for part 1. Here we spoke about the fundamentals of absorption. Then we spoke about the absorption isotherms, and then we spoke about particular cases of adsorption. So the definition of adsorption versus absorption. Absorption is not very key to the course, whereas adsorption is. As I said at the time, I'm not going to be too harsh on you for misspelling. If it's an obvious case of misunderstanding, I will knock off some marks, but if it's just a simple case of misspelling ad and absorption, I think I can forgive that. However, going forward for common knowledge, these are very different words. Well, they're related, but they mean very different things. Oh, and here were the definitions of the adsorption, absorption, adsorbate, and adsorbent. And that was further reiterating the difference there. Some terms here of absorption, desorption, and in terms of what the language that we used at the time. Then we spoke about physisorption versus chemisorption. Again, this is a topic that you should be familiar with, not only in this course, but other courses. We spoke about the difference in energies and how the energy and the separation distances vary for each type of bonding. Then we spoke about the Langmuir isotherm. So in terms of the Langmuir isotherm, you don't need to know this equation here, but you need to know this plot here. I'd also like you to know what type of units you could use. So this is concentration, this is absorption amount. This is normally measured in amounts, mass or moles per gram or per unit area. So that's that value here. Here are some assumptions of the Langmuir isotherm. Homogeneous sites of absorption, maximum of one monolayer. This is the key principle here. And there are no interactions. So it's an assumption. However, the maximum of one monolayer is the key one here. Then we spoke about BET and how we can now introduce a secondary layer, and how that is taken into account is the inclusion of a second heat of adsorption on the surface. Here's the two side by side. Again, equations here are not necessary. Knowing their approximate shapes, particularly Langmuir, is key. BET takes the shape of Langmuir and then has an exponential rise afterwards. Note, this is when coverage is 1. One layer coverage equals 1. Then we spoke about Traub's rule. What is Traub's rule? Or what is the effect of adding CH2 groups to a surfactant molecule in terms of its adsorption? We also spoke about Gervich's rule, which spoke about the competition of a solvent for the surface and how the heat of wetting of a solvent can affect greatly the amount of further absorption taking place. And included in here, although there were no green slides on it, was polymer absorption. And polymer absorption is also key as well. However, that notes that there were no green slides on it. However, there was information on adsorption throughout there. That is required for the exam. So yeah, if you do not take into account yellow slides, that's a potential stumbling block, a potential missing part of the course for you. Carrying on, adsorption. So we spoke about, so this was the summary of part 1. In part 2, we spoke about electrostatic interactions, and that is through the electric double layer and the de Baer-Huckel parameter. So we spoke about the electric double layer, how it's set up, what's the general principle of an electric double layer. We spoke about, again, general points and how it can be applied to curved surfaces. Helmholtz was the first layer, a rigid layer, held a certain distance away. And then this is kind of the simple diagram of what it looks like. The electrostatic potential here degrades in a linear fashion. And this is 0, which is when we reach equilibrium or bulk conditions down here. We spoke about the Gouy-Chapman approach and introduced the idea of a diffuse double layer, and compared the two, Helmholtz and Gouy-Chapman. Again, more comparison, a rigid layer in the Helmholtz, a diffuse layer in the Gouy-Chapman, a linear degradation or reduction in electrostatic potential. However, this is an exponential decay here. Then we spoke about the double layer thickness. The key thing is that the double layer thickness decreases as you increase the concentration of ions, was the key point here. There's some more general points on the Gouy-Chapman layer and how potentially the Gouy-Chapman, because it doesn't take into account hydration spheres, there may be some error in the modeling. We then spoke about the Stern approach, so this combines the Helmholtz and the Gouy-Chapman, where you have a rigid layer, but you also have a diffuse layer after that. So to compare the three, these I've already compared today. For the Stern layer, you have a linear decay, and then when you get away from the rigidly held ions, that's when you have an exponential decay here. So in simple terms, Stern combines Helmholtz and Gouy-Chapman. This was the learning outcomes, and I've already gone through those, so I won't take up any more time. Then chapter 5, which is materials fabrication and those sorts of considerations. So manufacturing of materials, what do you generally take into account? Again, this is a principle that it extends to other modules, the structure-function relationship, so how important is structure in the function of a material. My point being that it was quite important. And then we went through some methods here. So in terms of materials fabrication, we went through a sol gel synthesis of silica. We also spoke about, before this slide, amorphous versus crystalline silica and how you can change between the two. This is a key reaction. The synthesis of silica via sol gel is an important reaction I'd like you to know. We spoke about top-down and bottom-up synthesis. Again, I'm not going to dwell on these, but these are just different methods of making nanomaterials, one starting from molecules, the other starting from larger structures and breaking down. Then we spoke about spray coating, dip coating, and spin coating. Now for these, I would recommend remembering or learning, understanding the individual steps here. And so that's something that I would recommend that you do. We then spoke about physical vapor deposition, thermal activation. So this was the use of heat to vaporize a material and to deposit it. You can use an electron beam to do the same thing. Then we spoke about sputtering and how it was slightly different because it didn't depend on melting the material. ALD, so there are steps here and there's diagrams that I would encourage you to learn. CVD, again, there's steps here and diagrams, again, that I would expect you to learn and to be able to repeat back to me. Most of these methods make sense to some degree, so there is a principle of learning through understanding and not just remembering them. However, that's up to the individual. CVD can occur layer by layer or via island growth. There are conditions here, and we spoke about how the growth mechanism can affect appearance, where island growth scatters light and so appears opaque, whereas layer by layer is either a mirror-like finish or transparent. And that was the green slides from chapter 5 that we went through. Chapter 6, surface chemical modification. This could encompass Langmuir-Blodgett, a polyelectrolyte adsorption, chemical modification, and surface patterning via lithography. Langmuir-Blodgett, what is it? And that is a collection of amphiphilic molecules, as shown here. How they formed. They have different phases, gas, liquid, and solid. What does that mean? They are measured using estimated molecular area and surface pressure. What is surface pressure? What is molecular area? What do these look like? So these are collections of amphiphilic molecules. In each phase, what do they look like? Going through in more detail, the plots here. In terms of the details here, the key one here is the deposition pressure, which happens at the most condensed phase before solid, which is L2. And you can get some other details here as well. Langmuir-Blodgett transfer or deposition can happen horizontally or vertically. Then polyelectrolytes. So what is a polyelectrolyte and how it can affect the properties of a polymer if you incorporate a charged species on it. So again, more detail on polyelectrolytes. Polymers and electrolytes make a polyelectrolyte. Then we spoke about self-assembled monolayers and what needs to happen in order to make them on a surface. Oxidation state change and surface structure change. Then we spoke about lithography, so the general process of lithography. The reaction here is not important, but what I wanted to get over to you is that you can use etching and deposition in this type of process. Okay, and those are the green slides there. Obviously, there's more information there, but again, this is just a summary, so I'm just going through it as I am. Chapter 7, so this was one of the largest chapter, if not the largest chapter in the module, and this is talking about emulsions and also colloids. So this was also split into two parts. We spoke about the emulsions, the fundamentals, DVLO theory, emulsification methods, and emulsion stability. So again, reiterating what an interface is and how it can fragment into a dispersion. And again, more notes on dispersions here. Emulsions, so talking about their kinetic and thermodynamic stability. Hopefully this is, hopefully you know what I'm talking about here. And if you don't, then you should, particularly by exam time. The general structure of emulsions, what do we need to consider? So viscosities are important, and that those were talked about later in this chapter, but this is kind of what they look like. And there was a start of a discussion about the role of a surfactant here in terms of emulsions. So this was a summary of the effect of a surfactant. Generally, it prevents coalescence and reduces surface tension, that is, so that it can facilitate formation. Stabilization methods, so electrostatic repulsion, steric repulsion, and entropic repulsion. DLVO theory uses van der Waals and electrostatic repulsion, combines them into a plot. If you have electrostatic repulsion, you have a VM, you have a barrier, and then you have a V minimum down here. So again, this was discussing VM and V minimum, and again, more discussions on that. Here is a first mention of a secondary minimum and the effect of increasing and decreasing VM and V minimum here. This is talking explicitly about the effect of emulsifiers, such that they do not cause the formation of emulsions. However, they facilitate them and prevent facilitate their formation and prevent their coalescence. Then the introduction of Bancroft's rule and the selection of which type of emulsions we are forming. We related that to the CPP and introduced a new factor called the HLB, which is shown here. So hopefully from the tutorial 3, you can now start to understand the expectations that you in an exam situation. This in particular, the discussion of emulsions and interfaces and HLB values is important. Further into Bancroft's rule, and just a summary that high HLB surfactants provide oil and water emulsions, low HLB surfactants provide water in oil. A diagram of that shown here, so just showing you the preference for forming oil and water or water and oil emulsions. Again, another iteration on surfactant placement at the interface, and also the shape of the interface there. Introducing also the effect of temperature and electrolytes for tuning the HLB value indicated here. So here we spoke about explicitly temperature and the effect of surfactants, electrolytes, and how you can alter for some surfactants the apparent HLB, and therefore the type of emulsion that is formed by that surfactant. So that was the end of part 1. In terms of part 2, we are continuing emulsion stability, microemulsions, Pickering emulsions, complex emulsions, and phase diagrams. So here's where we kind of spoke about the selection of an emulsifier and general guidelines, and ended up speaking about the HLB value, but there are other factors here. In terms of stability, we spoke about the breaking of emulsions. So how do they destabilize? They destabilize in 2 main ways. One is by not changing their size, but collecting together, either by sedimentation, creaming, or flocculation. You can also get coalescence or phase inversion, and that happens in these ways here. This was the general mechanism for destabilization and breaking, and these are some counteractions here. Remember, I said that Oswald ripening, although important in the wider literature, is not so important for this course. Okay, and so note here that there were no green slides shown for Pickering emulsion, complex emulsion, and phase diagrams. However, they are still included in the examinable material. So that's just a note there for you. Chapter 8. So this was liquid fluid interfaces. And this spoke about types, surface tension versus interfacial tension, miscibility, spreading, and the measurement of interfacial tensions. Skipping all the way to miscibility, we spoke about what these terms are. Again, these should be terms that you are familiar with. However, they were defined here in terms of the course. In terms of miscibility, we spoke about how small portions of either liquid or higher temperatures could facilitate generating a solution as opposed to 2 different phases. We spoke about how interfacial tension relates to surface tension, and then spoke in detail on how these forces come about and how they relate to surface tension. However, there is another factor that we need to think about here, which is the interfacial attraction. So do these molecules like each other? Do they have similar bonding between them? And those sorts of considerations. Then we spoke, introduced or reintroduced the Wilhelmy balance, and then introduced the Young's equation here. Again, those were the learning outcomes for Chapter 8. Chapter 9, these were the learning outcomes. So this was the wettability. The key learning outcomes for this were the models, Young's, Wenzel, Cathy-Baxter, and the simplified Cathy-Baxter. Here's the Young's model, which is shown here. Again, these are the only equations that I expect you to know, simply because their presentation will provide. It's dependent on the model itself, and so Young's model, how it doesn't take into account surface morphology, and so other models are needed to do that. The Wenzel model being the primary of those. Again, I'm not going to go through it in too much detail, other than to say this is a key equation. The Cathy-Baxter equation here, again, this is something that you're going to need to know, and how it differs primarily through the inclusion of air. Again, more Cathy-Baxter discussion, and how it is complex, and then relating that to a simplified model, which was shown here in this form here. Again, this is a key model, a key equation that you need to know, and we'll need to use to conduct calculations. So those were the learning outcomes. As I said, the most important of those were the models. Then we spoke explicitly about superhydrophobicity and superhydrophilicity, surface wetting, superhydrophobic surfaces, and superhydrophilic surfaces. The classification of surface wetting via the contact angle, here, you should all be familiar with contact angle discussion. And so that's shown here plainly. Advancing and receding contact angles, tilt angles, and how you can measure advancing and receding contact angles and the tilt angle all at the same time, and what the tilt angle means for the wetting mechanism. Then I spoke about water bouncing. So why is it needed? What are the weaknesses in the contact angle measurements? Again, these are key principles. Superhydrophobic surfaces, so how do you make them? High roughness and inherent hydrophobicity. Knowing the wetting models, this should be relatively straightforward. This should make sense. How do you then go about that? There were models presented here, so in one step and then in two steps, and the sort of surface chemistry we were talking about. If I have time today, in the second bit of this session, I'll go through fluorinated materials and why they are still hydrophobic. Applications, so superhydrophobic surfaces, self-cleaning and oil-water separation were the two key ones that I pointed out. Superhydrophilic surfaces, a key thing about superhydrophilic surfaces is that materials with a high enough critical surface tension will be superhydrophilic. And so that's one thing to note, is that even for a flat surface, you can still have superhydrophilicity. So these were again, the learning outcomes, and I've indicated those there. Some of these weren't touched on in terms of the green slides, but they are examinable material. Chapter 11, adhesion. So we spoke about fundamentals, types of adhesion, factors, adhesive failure, measuring adhesions, and a real-world example. We spoke about the difference between adhesion and cohesion, the relationship between cohesion and surface tension. We spoke about if you have an adhesive joint, how there are three main varieties. That is mechanical adhesion, chemical adhesion, and physical adhesion. And so those are the three types of adhesion mechanisms. In terms of the failure mechanisms, you've got adhesive failure, failure of the adhesive forces. Then you have cohesive failure, that is failure of the cohesive forces. And again, there are things missing here that aren't on there, but are examinable. Chapter 12, talking about surface morphology. Types of surface morphology, techniques for increasing surface roughness, the effects of surface roughness, and the fabrication of smooth surfaces. So you can generate surface roughness by adding or subtracting material. That's etching or depositing or growth. And then we spoke about how the effects of surface roughness. I spoke in terms of hydrophilicity, but also gave you some other causes or other effects on that as well. Water pinning. So we spoke about water pinning and how the type of surface roughness can affect the ability of water to travel across it or to bounce on the surface there. The adhesion of bacteria on superhydrophobic surfaces. So generally, increasing the surface roughness increases a bacterial adhesion, but with superhydrophobic surfaces, we actually decrease the available area for the surface to attach to. Then we spoke about fabricating smooth surfaces and how this generally can't be achieved using abrasion or these types of methodologies. Instead, you need to do one of three things, and that is grow a material in a flat way, reorganize the material, or you can break apart crystal to show the crystal planes or the flatness of the crystal planes and expose those to be your flat surface. And again, the details of this are on a yellow slide, and the precise details aren't required. You just need to understand what is meant by here and those details are included on the yellow slide. Okay, so those are the learning outcomes there. The final chapter, again, this was a relatively long chapter, and this had a lot of information in it. So we spoke about the role of a comprehensive materials analysis protocol, analysis of composition, chemical structure, microstructure, and localized surface chemistry. So in terms of the comprehensive materials analysis, what is included in that? And here were three general things that we spoke about. This is a summary slide of the comprehensive materials analysis protocol. And bearing in mind that we were talking here in the context of having no long-range order. And these were the techniques that we discussed during the module. So EDX, how does it happen? How does it show you what elements are present? We spoke about electron diffraction. How does it work? And what is the result of it? Such that you can look at nanocrystals, and you can also look at the short range order within materials because there is a strong interaction. XAFs, so how do we measure XAFs? XAFs is a type of X-ray absorption spectroscopy. And so, yeah, how does this happen? XPS, again, the details on this, how does it provide us information on elements, but also you can get other information out of it. And then I gave you a slide on how you can summarize these techniques by breaking it down into probing, particle or radiation, the nature of the interaction, and what are we detecting at the end of it. So then, yeah, here's the same slide again. We spoke about AFM, and the AFM equipment and how that's used is on a green slide. Again, this is key information here. We spoke about optical microscopy, SEM, TEM, and that was the those were the learning outcomes for chapter 13. Okay, all right. So as you can see in the slide presentation, there are 192 green slides, well, minus the title slides and learning outcomes. There are a lot of slides that are green in terms of their information. So I appreciate the amount of work that it will take to revise for this subject. I do appreciate it. Yeah, so that was a summary. As you saw, that didn't provide any new information. It was just me going through it and jogging your memory of what the course is all about. And that has brought us nicely to the end of the first session. So in the remaining part of this session, what I want to do is open up the floor. So first of all, we're going to take a break because that was intense for me. I don't know how it was for you, but yeah, so we're going to take a 10-minute break, and then I'm going to open up to any questions you have, be that on the coursework, be that on any chapter at all. Any questions that you have, if you want more information, I've got my, I can use the whiteboard. I can go through that in as much detail as you want. And so that's what we're going to do after the break. Yeah, I can't remember if I said, but if there are questions on the workshop, please also include those. I will, because the deadline is today, I will make sure that I prioritize those questions for the workshop material. Yeah, so if you have any questions, please post them to the WeChat work group. We'll have a 10-minute break now, and then I'll come back to answer questions. Okay, see you in 10 minutes.
we'll get started again. So I've got one question. So firstly, a question on the coursework. 1 second. Let me make sure.
Make sure I'm in the right setting. Hopefully you can hear me better now, or you can hear me to start with. Firstly, a question on the coursework, and that is, can you use a cover page? So my answer is that it's fine to use a cover page if you want to, as long as it has no material that needs to be assessed. So that means that anything on the cover page, I won't be looking at from an assessment perspective. It won't improve or decrease your mark, but if you choose to do it, you can do it. I think is how I would say that. Anything on your cover page, anything on the cover page, I would not be assessing. So yeah, hopefully that's clear. I'm just going to switch over to the other group and see if they have any questions there. Okay, and there are. I think that's So there are. There's only one more question that I can see, or maybe there are more coming in. Yeah. When we add our names to the names and numbers on the cover pages. So the point that I wanted to, so the thing you have to have, let me go through what you need to have. I'll just share my screen. This one here. So in terms of the assessment, this is what I'll go through. Is it this one here? No, it's this one here. Yeah. So this is what I mean by so how do you reference the course slides in your coursework? So what I would say is just do it if you what I want to highlight with that. So the subject matter is introduced to an excellent standard. This includes substantial reference to the literature and demonstrates an understanding relating to the assigned task. So the key point is here. So the literature refers normally to peer-reviewed scientific literature. And although I like to consider myself an expert, my course is not peer-reviewed literature. And so what I would say is I would encourage you to use external references where possible. However, if you've already done that and you just can't find a source for a particular piece of information, then please cite me in whatever way you can, as long as it has an indication of the course and where you got it from. I'm happy with that. However, to caveat that, reference to the literature is an assessment point. Okay. I have a question about the failure of adhesive junctions. So let's cover the adhesive junctions, and then I'll respond back on via text. So this relates to this slide here. Let me just present it in full screen. So the question, this is from the polymer group, is why B can regard as a kind of adhesive failure. Could you please explain this? So that refers to this one here. And so what type, so the question is what kind, as a kind of adhesive failure. So let me go to the whiteboard to answer this in slightly more detail. I think I'll do that. I think I need to find this pen. Oh, that's fine. All right. Okay, so just to go back to what B looks like, it looks like that. Let me draw it in an exaggerated way. Okay, and here, blue, we have a chunk there and a chunk there. And these are the pulling directions indicated in the diagram. So to start with, this is the type of question that probably won't be in the exam paper, being that I would present you with a very complex pattern, and then ask you whether it's cohesive and adhesive failure. As I said in class, I would expect you to be able to define adhesive and cohesive failure. So the point is here is what we're asking is it adhesive failure or cohesive? Oops. Stop doing that. Okay, there you go. So the question is that where was this side and then where was this side? So what does the original case look like is my question. So let's just draw an adhesive junction. And this is where it gets a bit like a puzzle. And again, I'll draw in. Okay, so does this break happen here? And then this and this refer to the colors that I've shown here. So this, if this is the case, this would be some type of cohesive failure. And then this would be some type of adhesive failure. And so what I'm trying to point out is that this case is complex. Or does it look like this? So is it like this? And it's simply come away in this fashion here, where it's just come away like this. And it is strictly a cohesive failure. I've drawn that in the wrong color. So that would give you a similar pattern, but it depends how you want to see it. So the way that I see it in the image is that this has come away from here and this has come away from here, and this middle bit is broken as well. So it's a mixture of cohesive and adhesive failure. However, it's a static diagram with no further explanation. So I'm happy for you to interpret it however you want. Yeah. So that's my my take on that question. Yeah, but as I said, you don't need to know that. So you don't. So I will not present you. It's very unlikely I will present you with a degraded material with very little information and ask you to characterize it. If I'm asking you the question, then I would ask you it in this type of form and have more discussion about it. However, I'm not going to present you with a simplistic diagram and ask you to interpret it. Yeah. Hopefully that helps. All right. I'm just going over to the other group to see if there are any more messages. So I think that's it. I think that's all I can see. Unless I'm missing something. Oh, I've got a message here. So there's a question asking about sol gel formation. So this was in the summary slide, which I showed here. And that relates to chapter 5. Yeah. Oops. So the question is that do you need to know this? It's a green slide. So yes, it's a short answer. Yeah, I'm going to need more information if that is the question. But I would say, yes, you do need to know this reaction. You also need to know, I'm not going to expect you to replicate this exactly, but you do also need to know these reaction steps here. All right. So that's all I can see. I mean, maybe I'm missing something, but it makes me somewhat hopeful, or that you're all too busy with the coursework. So what I'll do is I'll stop talking. If you do want me to go through anything, coursework, revision, whatever, let me know, and I'll check in just to make sure that just to make you sure that I'm still here. And I'll come back when there are questions. Okay. I'll speak to you in a bit.
Hi everyone. Someone just reminded me that I was going to talk about fluorine bonds. So that's what I'll do while we've got some time. So I'm just getting my stuff together. I'll go over to a whiteboard. So just for information or completeness, let me just also make sure I've got the right settings so you can all hear me.
That should be okay. For completeness, what we're talking about is the synthesis of hydrophobic materials, which is all the way down here. And that refers to this slide here, which is saying that, it appears earlier, but this is the first time it appears on a green slide. And that is that hydrophobic materials also include carbon-fluorine bonds. So that's one thing that I'll go into. Note that this is not examinable information, other than the fact that carbon-fluorine bonds are hydrophobic, or carbon-fluorine materials are generally hydrophobic. What I'm about to go through is not required for the exam. And so that's something that I want you to bear in mind. So if you're not interested, you can stop listening. But for those that are, here we go. So just for context, what we're saying is that PTFE is one of the most hydrophobic materials known to man. So that's where we have fluorine bonds connected to a carbon chain. This is polytetrafluoroethylene. So ethylene, this is this unit, tetrafluoro, and it's a polymer. So this tends to be a thermoplastic, so that they're just long chains and there's not a high degree of cross-linking. However, there are other ways of forming this, but generally it's a thermoplastic there. So the good thing about this is it's very stable. So carbon-fluorine bonds are very strong. It's also high bond strength. And its environmental stability. Stability to things like UV. UV. Also has for a polymer has a high temperature resistance, but also it's hydrophobic. That means that the Young's contact angle, water contact angle is around 120 degrees. It may be higher for some materials. Note that this is a flat material. So knowing what we know, so if we look at the carbon-hydrogen bond and we imagine let's go through here. And we question this. So we question what is the polarity. And what we find is that carbon and hydrogen have very similar electronegativities. And so there are no real dipoles to speak about in carbon-hydrogen bonds. I think that there's a slight delta positive on hydrogen, but you'll need to check that. In fact, let's see if we can get an electronegativity table. So what I'm talking about here is this. Let's open this in a new tab. So this is a periodic table. However, what we can see here are electronegativity values. So these are simply how many electrons does this material want. So if you look at hydrogen and carbon, carbon has a slightly higher electronegativity, meaning that it wants more electrons. It wants electrons to a higher degree than hydrogen. And so, yeah, I was correct in that hydrogen, because it's less electronegative, means that it is slightly delta positive. If we look at carbon fluorine, so fluorine is the most electronegative atom in the periodic table. It's almost twice as much as electronegative as hydrogen. So that means that our carbon fluorine bonds are going to be very delta negative in terms of the carbon fluorine, in terms of the fluorine rather. So what we have here is delta positive and delta negative. So this is polar. So the question is that this is a polar material, however, it is also hydrophobic. So how do these things come around? So just to caveat what I'm about to say, this is a very complex idea, and there are many theories in the literature, and I'm going to present my idea on them, and you can agree or disagree, but what I would encourage you to do is to look into the scientific literature. So what I want to talk about is the availability of water to interact with this dipole primarily. So we've got water here. As we know, it's delta negative and delta positive. And so if this happens, then we have a very strong possibility for interaction. However, how likely is this? So if we look at a carbon fluorine chain, so yes, it looks like this when you draw it like this, but in reality, what you have is a carbon. Let me draw it in scientific form. Let's do it like that. So then we have fluorine here, and we have right here, fluorine, fluorine, fluorine. Okay, and then we can just label this fluorine just to be simple. So if we label this delta negative as blue, then what we have is a cloud, an arrangement of delta negative. So, and fluorine atoms are rather big. And so what this means is that we have a big area of delta negative. So what that means is that if we have a water molecule, it would need to arrange in this way here. And there's some evidence that it does do this. However, this is not a stable conformation, and I'm going to tell you why. So, in terms of water and its arrangement in terms of binding to a surface, what it would be good to do is to look at water in its molecular form. So then we have also two lone pairs. which extend this way. So this is a tetrahedron. So again, tetrahedron would look something like this, with two of these being lone pairs in the water's case. And the reason why water forms such strong bonds is that it enables the sharing of its electrons with other water molecules. So just for simplicity, delta plus, this is delta negative, and so it shares electrons into the water. So this is a reason for it being a stable and very favorable interaction. If it gets cold enough, as we've seen in the course, it will freeze and form a regular crystal structure based on the most efficient way of organizing these types of interactions. So the passing of electrons from oxygen to hydrogen, fundamentally. So that's part of why water, attraction of water works. If we do the same thing with fluorine, so I'm running out of space here. I can just draw it. I'll draw it here. Let's delete this. Now redraw that water molecule down here. Yeah, so if we do a fluorine, what we have in the case of fluorine is 3 lone pairs. Now, the way that these lone pairs are different, so they are somewhat hybridized, but that's not highly important. But it is discussed in the literature. But what we can imagine is that we have lone pairs here that we want to bind to. So this is delta negative. However, because of the electronegativity being very, very high, what that means is that these orbitals are very contracted, so that they are not formed like this, but they are formed like this, and very close to the center of the molecule. What this also means is that if we have a water molecule coming in with its delta plus, and we imagine sharing this, there's not going to be much movement of electrons from the fluorine. And so in general circumstances, these electrons are available for sharing, that being moving from one location to another, but albeit temporarily, to neutralize charge and be stable. Whereas it does not happen here. So the water, although there is some level of electrostatic interaction, the water molecules cannot get close enough, and they are not delta positive enough to rip away this electronegativity or the electrons from the fluorine. So what that means is that the water molecules cannot arrange in a stable way. They may have some electrostatic interaction with them, but they cannot interact in a favorable way. So the only interaction is via van der Waals forces and not via hydrogen bonds. So to briefly contrast this with the case where we have a carbon-hydrogen bond, now remember in this case we have a delta positive and delta negative. We're considering the opposite case here where we have a delta negative and delta positive. what we're able to do in this case, because oxygen is not as electronegative, is share electrons to the hydrogen. This happens in a very low amount. However, it happens in a higher amount to what we see in the fluorinated case. And so that's the reason why fluorine is more repulsive to water. And that's because this type of interaction, that the relative sharing of electrons, cannot happen with fluorine. However, even with alkyls, carbon-hydrogen bonds, this sharing can happen to some degree. And so that's the reason for it. All right. Hopefully that answers the question. And hopefully the person who asked me that question is here. Yeah. But to caveat this, to those that were listening, this is not required for the course. It's very interesting. The reason why I don't teach it is because there's a lot of orbital theory involved. And so it would detract from what we currently teach in the course. But that's the reason why fluorine is hydrophobic, or carbo. Carbofluorines and PTFEs being one of the most hydrophobic materials ever made. Okay, so I'm guessing that suffices. All right, so we have 10 minutes left of the session. If you do have any questions, again, post them. I'll come back if I don't receive any questions. Come back at the end just to kind of summarize what we do from now, and then sign off and speak about what's to come. Okay, so yeah, I'll come back towards the end if there are no questions.